Hello everyone, good evening. Thank you for joining with me. I'm Vaishnav Achath from Texas Instruments, and today I would like to talk to you about a proposal for a remote processor framework in Zephyr RTOS. I work with the Linux team at Texas Instruments and primarily working on Linux and U-boot for TI processors. TI is a part of multiple open source organizations, including Zephyr RTOS, and we focus on upstream and open source ecosystem in our device definition phase itself. So as part of my day job, I work primarily with Linux and U-boot on TI devices. I am also the maintainer for TI platforms in Zephyr RTOS. So here are a few disclaimers. So this is just a work in progress proposal and get the community feedback on the proposal for a remote processor framework, why we thought we need a framework in Zephyr RTOS. And this is not a complete implementation, and we'll be working on a RFC and the standard process for introducing the subsystem once we gain sufficient feedback from the community. Okay, this is how the talk is being spread out. So first we'll go through what is remote processors, then the motivation of why it might be useful to have a remote processor subsystem in Zephyr RTOS, and we'll also discuss on existing ways of managing remote processors in Linux and U-boot, and how that does not cover all the system level use cases. Then we can discuss on how we can introduce a remote processor framework in Zephyr, both in client and also in host mode, which we'll discuss in detail and more. And also we'll have the benefits of having something like this and future plans, what we are working towards. Okay, what is a remote processor? So unlike traditional microcontrollers and microprocessors, where there was a single CPU core or multiple CPU cores of the same type working in SMP or symmetric multiprocessing mode, today's processors are very complex and have a heterogeneous architecture with the same SoC, having multiple application cores, multiple real-time MCU cores, then multiple low-power MCU cores, and sometimes system controller cores, DSPs, and so on. So remote processors are those processors in the system which is managed by the host. So it's we kind of think like it's always the application processor or the biggest processor in the system as the host. It's not necessarily true that the biggest processor, maybe the application processor running Linux, is always the host. So for example, if you take the case of a bootloader, which boots up multiple cores in an AMP system, so you can think of the bootloader as a host which boots up all these remote processors, others. So let's say in case of our devices, we have a startup core, a Cortex-R5, which boots up the Cortex A53 or A72 cores. So in that case, we can think of that Cortex-A core as a remote core with respect to the bootloader. When you come to Linux and you work with like maybe you have a DSP accelerator core, or you have a real-time MCU core, then those cores which you manage from Linux are the remote cores when you look from that perspective. And today there is a very mature framework in Linux and U-boot for the management of remote processor cores. So from Linux or U-boot, you can start, stop, load the firmware, shut down, or even attach to a running cores and do all those kind of functionalities. And Linux also has some advanced features, like you can start a communication channel through the standard RP message framework, and also do some advanced features through the RP drivers. So for the discussion, in this discussion, we'll be having some implementations or demos. So we have taken a TI AM62 platform as a reference, and this has a application processor Cortex A53, and a remote MCU, a Cortex M4F. So traditionally we use systems where we just boot up the M4 from U-boot or from Linux, but in the end of the system you will see how we have able to get both of these cores running Zephyr, and how we boot and load the remote processor from Zephyr. So you might have a doubt, why even use Zephyr on application processors? So those are designed with an MMU and the complex pipeline to run Linux or a high-level OS. And while in most cases Linux is the popular choice for running on application processor due to the versatility. Zephyr RTOS can also be a good choice you can run on the application core because Zephyr supports SMB symmetric multiprocessing support on Cortex-A with the 64-bit ARM cores, then gives you real-time performance. Then there are complex subsystems like networking, graphics subsystem, display, USB, everything, which you might not get from some of the traditional RTOS where you might not even have a device driver model and all. Then Zephyr also have some features like power management, which might be suitable for. So it's kind of sits in a sweet spot where you don't want the complexity of Linux, but you want a lot of features that Linux also offers. And also it's much simpler to configure and develop than Linux, and you have a much smaller application size. So most of the times everyone prefers to run Linux on a high-level OS and on the application cores. But on some systems, you might need deterministic behavior or real-time behavior, and you need to switch to the preempt RT or the real-time Linux kernel. The real-time Linux provides the versatility and rich ecosystem that Linux provides, along with the real-time deterministic behavior. But Linux and real-time Linux are much more complex, and you have multiple tuning knobs that you need to configure properly for your system to get the actual deterministic performance. Zephyr is much simpler, and even though it's not as versatile as Linux, it provides a necessary subsystem like we discussed to implement complex use cases like networking, graphics, display, USB, and all. And also, if you look at Linux or real-time Linux, the device drivers that's being used in real-time Linux is exactly same as what you have for the vanilla Linux. So you might not have thought of a proper real-time implementation for your device drivers. So even though you adjust all the tuning knobs for real-time Linux and perform all the optimizations, if you have not implemented the device drivers properly in Linux, you won't get the deterministic performance. But if you look at Zephyr, you will have the mindset that it's an RTOS and you are implementing the device driver to behave in a deterministic manner. So we have had previous debugs and issues where we did not get the proper real-time deterministic performance from the device driver. So the kernel, the scheduler, everything provides you the real-time performance. Sometimes you might not get the determinism from the device drivers because you did not implement the device drivers for a real-time system. You just implemented for the normal Linux. But that's not the case with Zephyr, but you develop with an RTOS mindset, and from the day one you will be implementing that in a way that you have the real-time performance for the device drivers. And now, so that why Zephyr can also be used in application cores. Now, why even have a remote processor subsystem in Zephyr? Why not boot up all the remote cores from bootloader? So we saw that U-boot supports. So why not boot up all the DSPs and all the remote cores from bootloader and just forget about it? So that's where, U-boot has a very good subsystem where you can load the remote cores, even boot up Linux, the DSPs, everything. But for some use cases, you cannot just have the remote cores booted up initially and just forget about it. For example, you want to do power management. So the system is choose to suspend when there is no activity. And when it resumes, you need to resume the remote processes also. But consider the case where you don't have Linux in the scenario. So you have Zephyr running on your complete system, Zephyr running on the host processor, and Zephyr running on Zephyr or maybe another RTOS running on your remote processors. Then what happens is when you resume, you don't have a proper management framework to start up these remote cores and load the firmwares. But maybe just do a plain startup from U-boot, you have the necessary framework over there. And power management is very important feature that you will need to implement in most of the production use cases. And in this case, if the Linux was the host operating system, then you can have there is already a mature remote proc subsystem, and during resume, you can choose to reinitialize and reload the firmware and start up the remote cores. So coming to the motivation, so we always see Linux or real-time Linux in use cases. So we are looking at a hypothetical use case where we have application core running Zephyr, and you have a high-resolution display with multi-point touch, which needs to provide a rich HMI interface. Then you can have networking and communication protocols like Ethernet and CAN, and then you can have separate remote processor cores running Zephyr, doing some real-time tasks like motor control. You can have DSPs running workloads, so you can capture images on maybe a factory line and do analysis on a conveyor and do things like that. So traditionally, due to this, since something like a remote processor subsystem is not available, you can maybe do some of the features and implement this with Zephyr, but even though Zephyr provides the subsystem, we find some difficulties in getting these implemented. And also Zephyr has a very rich networking and the communication protocol stack, and we get the sweet spot between Linux and the traditional RTOS, where you don't have those rich frameworks, but you don't need to go to Linux for the complexity. So now we kind of understand why, or the motivation behind why we need the remote processor subsystem. So let's take a look at the Linux remote processor subsystem to gain some inspiration and how we can take the implementation as a reference. So Linux has a very mature remote processor framework starting maybe 10, 15 years ago, and it's a host implementation which allows you to power on, load firmware, stop the remote processors. And the framework is there so that you can abstract the hardware level differences. So the SoC vendors way of starting the remote processors might not be the same for the other SoC vendor. So you need to abstract away and give the common helper functions which the different SoC vendors can implement in their particular drivers. And in addition, the Linux remote proc framework is very complex and has some very complex features like the ARMv7 R devices, where you have a standard transport and platform-specific remote proc drivers only need to provide some low-level handlers, and the ARMv7 drivers will just work. So for example, there are things like ARMv7 TTY and all, like, which gives you an ARMv7 UART over the ARMv7 transport. So it will just work if you have the proper entries and handlers in your firmware. You don't need to do any plumbing in the Linux kernel to get this working. So you just need to advertise in your firmware. So the subsystem is just split into, so there are core functionalities like starting, stopping, and preparing the processor. So we'll discuss on each of these functions in detail so that we can take inspiration from this and implement similar ones in Zephyr. And there is also an ELF loader, so we need a cross-architectural ELF loader. So in these heterogeneous systems, you have maybe one of the cores as the host, and other cores where you need to load the firmware might not be of the same architecture. It might be a different architecture. So there are VirtIO helpers and the character device implementation. Those we won't go into deep because that's not relevant to if we want to implement it in Zephyr. So what's the minimum thing that you need to have in your remote processor client firmware to have it loaded and processed by a remote processor host? So the standards are governed by the OpenARM project, and there is something important called the resource table that the client firmware needs to advertise or provide it in the ELF binary. So the client firmware needs to have a section called resource table in the predetermined format, which that standard is governed by OpenARM. And so this is how the resource table looks like. So the resource table has a header where we have fields like the version and the number of resource entries. And each resource entry is also a structure where you have each resource entry has a header which determines the type, and depending on the type, it might have the contents. So what are resource entries? So resource entries are sometimes just telling the host that, okay, we have these capabilities. Sometimes we want to negotiate and get something from the host. For example, if you just start up a remote processor client firmware, you need to sometimes ask for some carve-out regions in the DDR, which the host is managing. The host can allocate this region for this particular remote processor and share the address and the size of the region as a response. So the client advertises or asks what it needs through the resource table structure, and this is how it's laid out. We have a common resource table header, and each entry has a header which has its type and data, and depending on the type, we are passing the contents of the resource table. Now we are going to look at what are all the operations or the API that the remote processor subsystem in Linux implements. So first one is the remote processor operation prepare. So you need to load firmware and start a processor to run. But to load firmware on a processor, you might need to maybe do some initialization before even starting to load. Think of it as switching on the processor. So if you have a heterogeneous processor and the remote core might have SRAMs or TCMs or local memories that you need to power on this, and also to avoid leakage, you don't power on anything in a multi-core SoC if you're not using it. So you need to power on this core and those regions that you need to load the firmware first before loading the firmware. So this is kind of a step as a prerequisite before loading the firmware. So this will be called before loading the firmware and before starting to run the code. So this is how you implement it. So sometimes you might even need to just set the TCM or SRAM to 0. You need to do a mem set and clear the stray values in the memory. So that's what the prepare function does. So now one of the most complex functions is the load function. So you have a ELF binary that you need to load, and the ELF will have different sections that you need to load to different parts of the memory. Sometimes these sections could be in the DDR. Sometimes it could be in the TCM or the internal SRAM or the IRAM, and it could be different sections. The complexity arises when you are loading it from a different processor, and both of the processors might not have a same view of your system. So if you look at a standard ELF loader, you just read this section headers, ELF header and section headers, pass through the section, and just do a mem copy and load it. But if you want to load to a remote processor of a completely different architecture, and it might have a different view of the complete SoC memory map. So the address 8000, what the host sees might not be same as what maybe it might be the address 0 for the remote core. So that's where you need to have a custom implementation of something called DA to VA. So that's the device address to kernel virtual address. Take for an example, your device, the remote core has an TCM or SRAM, which has the address 0 for an example. Now, if you look from a host, which is another processor, your SoC will have a TRM where you will see the memory map. So this TCM or SRAM might have a different address when the other host client processor sees. So the DA to VA is the mapping that you provides to map from the host's view from the device view, because the ELF sections will have the device view implemented in there. And then also there will be DDR sections. You might need to load it in the DDR section so that you just map and return the address. So you looked at load, and a load had a dependency. You need to have a translation. Now you have loaded the firmware in the expected regions that the core expects. Now you just need to start the processor. Now this also is it's very specific to your the vendor's implementation of the process. Sometimes it's just releasing the reset. Now if you go into deep how the releasing of reset, some devices, it might be writing to a register to release the reset. Sometimes heterogeneous processors have a system controller which manages all these things, and you send a message to the system controller, and that does release of the reset. So that a central entity controls the power, turning off the power, and reset of the entities in the SoC. So you do your SoC specific, the core specific implementation in your start function. Now you have started up the core, and you need to stop the core. So here also your SoC will have specific implementations where you need to follow. So let's say I was talking only about the remote cores being a single core. Sometimes it can be a cluster of multiple cores, and you might need to do some sequencing when you need to power off or releasing the processor. So you implement all this in this function. And now we are coming in a symmetric manner. We prepared, we started, we load the firmware, start, then we stop, and unprepare is just a symmetric version of prepare, where you release the resources and power down the processor. So now we have discussed on how the host implementation of remote processor is in Linux. But Linux cannot ever be a remote processor client. Usually it's always only the host that manages the other remote processors. But if you look at Zephyr, it runs on Cortex, big application cores, to smaller Cortex-M microcontroller cores. So it can be both a host and a client. So we are just discussing about the client interface. Zephyr already supports this, so we can have the firmware compiled with resource table and load it to a remote processor. It's all using the helpers from the OpenARM library. There are already implementations, so there are platforms reusing it, and one of the platforms I took for the demo is also implementing something like this. But we are, since we don't have a framework, we are duplicating some of the code, and each platform is implementing on their own implementation. For example, I just did a grep of resource table, how different platforms are packing the resource table to their images. So if you look at 7 or 8 platforms there, they're all packing the resource table and having their own implementation, where the resource table is a standard entity that's governed by the OpenARM standards, and you don't need any specific implementation for your platform. So you could just have a common linker include and things like that to make this process efficient. Zephyr already supports the client mode, but we want to have some advanced features. So you have, we discussed about the system suspending. So you cannot sometimes abruptly stop a running remote core. So the remote core might be holding resources on your heterogeneous system, and if before you stop the core, you need to have some negotiation and let the remote core properly release all the resources it has requested, and then properly do a shutdown. That's called the graceful shutdown feature, which we have to implement on, not on Zephyr, on one of the other RTOSs for our customers and in our SDKs. But if we had a standard framework, we could use that framework to combine with the device driver model in Zephyr and do a cleanup before doing a shutdown. So Zephyr, since it has a device driver model, it's very easy to hook something like this to the existing helpers in Zephyr. And also now, even though there are some implementations using Zephyr as a remote processor client, we need to have some implementations where, so we discussed the resource table. So the client can request resources and entities from the host and get those as a response and do the implementation. We have some implementation like RP, remote proc TTY and all, but we could improve that implementations to have advanced features like memory carve-outs, which is very important when you are working with DSPs. So you need to have memory carve-outs to do the processing and do the inter-processor communication. So right now what we are doing is a static allocation. We have a static, we carve out memories, we are statically allocating. We are not negotiating with the host. Now the host can be Linux or Zephyr, but in Linux also the host has the ability to do something like that, and Zephyr also can do that, but we don't have a common reference or example, or the framework does not support it. So now we looked at the host and client implementation. So I have tried to implement something like a remote processor host implementation. So this will just expose some API functions. So we discussed on how it was implemented in Linux. So again, this is not the version I might be putting in the pull request, or we are just looking to get feedback and get to some proof of concept that's working. So we are just implementing the host implementation where you have prepare, unprepare, then the start, the load, and the device address to virtual address conversion. So if you look at prepare, so I'm taking a TI processor as an example. So I'm taking the A53 application cluster running Zephyr in SMP mode as an example as the host, and the M4 MCU as a client. So if for prepare, so this device has something called a central system controller, to which you send messages to tell you need to turn on this power domain. So you don't have your host going and writing registers to power on or power on things. You just send messages to the common entity, so that you have a common entity that manages all the resources, power, clocks, everything in the system. So that's what so if you look at prepare, what I'm doing is I'm turning on the device power domain, because I need to write to the internal SRAMs of the core. And also I am holding the device in reset, so that whenever I load the firmware, I don't want it to be in a running state. And in start, what I'm doing is I'm just sending the message to the system controller to release the device from reset. And in unprepare, we are just going the reverse. We are turning off the device. Now coming to the complex part of the ELF loader. So I was looking at how we can process ELFs in Zephyr. So I looked at it and I saw that there was already an implementation using the LLEXT implementation, where they're already using the ELF headers, and there are some helpers that we can reuse. So there is also another place where you have ELF helpers in Zephyr, that's from the OpenARM library. So I'm not using it from the OpenARM library now. I'm using the in-tree, the LLEXT version. So if you look at how the ELF loader is implemented, I'm not sure if it's visible. So if you just do a sanity check of the ELF and you iterate through the sections and you try to mem copy and load the different sections of the image. And sometimes you might also need to clear the some of the sections that are not filled, does not have full contents. Now, when you want to load it, you need to have a device address to virtual address translation, because your host's view of the system memory might not be what is in your client's or the remote course view, which is what the ELF is having. So this is the implementation I have now. So just summarizing, we have the remote host, which allows you to boot and interact with other course running firmware with a resource table. And host support is exactly similar to what you see in Linux or U-boot. Linux has a much advanced implementation, but we are just focusing on just booting up the course and stopping the course. And client mode, there is already supports, but we think we can improve using the helpers provided by the OpenARM libraries to have more things like the negotiating for carve-out memories, doing graceful shutdowns and things like that. And also the client firm, we saw that every platform is just duplicating the linker commands. We could have had a common linker command. So things like that is what we wanted to optimize using the client framework. So now coming back to, we discussed some why the motivation behind introducing the framework in Zephyr. So MCU boot has a Zephyr port, and it could, if we have a remote processor framework, it can reuse the same drivers, and you can have it as a standard open source, very lightweight bootloader for AMP systems. So if you look at some of the DSPs offerings, we have some RTOS-based bootloaders where it's not based on Zephyr unfortunately, but it can even boot up all the remote cores, and it can even boot up Linux running on an application core. So there is actual need for a lightweight bootloader which can do a very fast startup. U-boot has a lot of sequential phases which steals a lot of your boot time, which sometimes you cannot afford on some of the production systems. And also, like in introducing the framework is not to duplicate the host and client mode implementation, so that each vendor can add their own implementation without duplicating it. And also we can enable applications with different kinds of cores working together and running Zephyr at the same time. Before it was just Linux and Zephyr running on some of the cores, maybe we can even have Zephyr running on all of the cores. So I have some demo. I have running on AM62x-SK. So we told that it has an application processor, A53 cluster, and also a M4 MCU clusters. So today what we can do is we can load firmware on it from the remote core from U-boot. So I'll just show what we are doing from U-boot. I'm hoping it's visible. So we are at the U-boot A53 console. And what I'm going to do is I'm going to fetch the remote processor binary. So I'll be running Zephyr on the left side. That's the A53 application processor console, and on the right side the console is empty. It's the console from the M4 MCU cores. So I'm fetching the binaries from over the network. So I'm just doing so. U-boot has a command line interface where you can do help some remote processor functions. So I'm just listing down, and it listed that there is an M4 MCU application, MCU core. So I just, so we looked at the sequence of functions. So we stopped the core. So we prepared it for loading. We fetched the image, and we are fetching two images. The first image is for running on the M4 core. The second one is for running on the A53 core. So I'm starting the remote core. You can see that the Hello World application with the console shell access has booted up on the right side console, which is the M4 MCU core. And on the left side, you can see that Zephyr is running on the A53 application core as well. So this is what we can do today with Linux, U-boot. So now let's look at I showed you how the API for Zephyr was implemented, and we'll look at how the same thing happens. So right now what I'm doing is I won't be running any remote pro commands from U-boot. I'll be just fetching the firmwares and just using the remote pro commands to boot Zephyr on the A53 application core. The Zephyr application on the A53 core will read the binary and go and load the M4. So I am just fetching the binaries. So we need to get two binaries because for first one we are running on the application A53 core, and the other one you are running on the M4 core. So earlier I had run, so you can see how fast that the M4 core start up from the applications, because you are not booting sequentially from the U-boot, but we are starting it from Zephyr. So the Zephyr has booted up from the core. So I have some debug logs. So first thing we are doing in this application is, I told you there is a system controller that we need to negotiate with to do resets, powers and all. So first we are talking with the system controller and printing out the version. Then we are requesting the processor handle, powering up the processor, and putting it to reset. Then do the ELF loader, load the ELF sections, and then release the processor from reset, and the example runs on the M4. So coming to the open items and future plans, so this is just a proof of concept we have, and we'll be working on an RFC pull request and describing on what the benefits are, and we need to add test cases, and we need to do it present in the development review for getting a new subsystem. And we are also exploring on how we can optimize and improve the client implementation to do things like graceful shutdown and resource requesting and negotiating resource to the host. And also what we would like to really explore is how can we have MC boot as a standard, very light bootloader for a complex heterogeneous system like those devices you saw before. And now I'm using the ELF helpers from the LLEXT implementation. So I talked with a few people from the OpenAM, and they told that there are already implementations and ELF helpers there. So we'll be exploring if we can reuse them as well. So now the ELF loader was written from scratch, taking inspiration from the implementation Linux. So most of the implementation we took from was Linux, and the OpenARM is the governing project that provides the guidelines for the remote processor framework and all. So we got into the discussion of this framework when we tried to add support for one of the platforms, and we were reproducing existing linger commands and code, and that Carlo was the person who suggested if it might help if we have something like this. So these are my contact details, and I'm available for any questions if you have.
So if I got this correct, you start the first Zephyr,
Yeah.
and then second Zephyr has, the first Zephyr has this application that starts the second one.
Correct. Yes, correct.
And how does first Zephyr knows where's the image for the second
So
one?
right now I am just hard coding those, so we can have it help us to read it from Flash, or we can have it in device tree. Usually in a bootloader's perspective, it will be in the boot medium, maybe an SD card or flash memory.
Okay.
So in this implementation, what I'm doing is I'm loading it to the DDR from U-boot, and I'm just reading it in my application.
Very good talk.
Yeah, thank you.
So I believe on these processors, TI has some clocking firmware that needs to run. I'm not sure what the name is, right? But there's something you need to do to be able to service the clock tree structure to turn clocks on and off. So is that an object file that you're linking into the Zephyr image, or does that exist somewhere else when you're running on the M4?
So when we go and do the MCU boot path, where we want to have the MCU boot as a bootloader, at that time we'll need to think about loading this firmware. So what I'm doing is I'm starting from the U-boot console, where all of these the device manager firmware, the security firmware is already loaded. So when we want to have the MCU boot as a bootloader, we need to have a way to have slots and load all these firmwares to the remote processors. So again, how U-boot does is also through the remote process framework. So if you look at the system controller or the security controller, the firmware is usually loaded by the ROM, and the power management, the clock management, the device manager firmware is loaded from the U-boot. And on these devices, it's a Cortex-R5 core, and that's also being loaded through the remote processor framework in U-boot. So if you have a framework in Zephyr, so you can either pack the binaries like U-boot does, or maybe have slots in additional slots in the MCU boot, the flash layout, and pick the firmware from there. We have not explored something like that, but if you need to have a standalone bootloader, we need to do something like that. Since I used U-boot, all of those are loaded by U-boot already.
Do you have a real use case in mind with that, or just exploring for now?
So we are exploring. So we have real use cases in our SDKs with the different RTOS. So we are trying to achieve something similar here.
Okay.
Yeah.
Any other questions?
Okay. Thank you. Thank you everyone for joining.